Hello all of you, my name is Ankit. I'm from IIT Bombay, and on behalf of all my research collaborators, I'm going to present my work on STYLIP, that is a multi-scale style condition prompt learning for clip-based domain generalizations. So these are some outlines of our research work. So the motivation behind using of our research work is like we have used the clip for better feature extractions and learning the style and content information from the inherent part of inherent intermediate layers for the domain generations, and we have used the clip without fine-tuning it, and finally we learn the domain and class distributions from distributions for the prompts that should be domain agnostic. So these are the problem statements lies like we learn the domain unified prompt learning for the style and content informations. We learn the prompt tokens from the various scales to learn the domain knowledge by using batch norm features from the frozen clip vision encoders. We incorporate multi-scale visual informations from the prompt for the prompt embeddings, and if this effectively reduce the overfitting and promote generalization across the different categories. So this is the general architecture overview of our styling, where we can see there are content projectors, and then there will be style projectors which we defined as a P1 to PM, and then these projectors are these style projectors are the embeddings from the style projectors are passed through the frozen clip, and to learn to learn in the contrastive manners. And in the right hand side we can see directly like how the different prompt learning techniques has been developed over the time and how we are different from it, and the and as I said, like we have used the batch norm features from the intermediate layers of the frozen clip vision encoders to generate the prompt embeddings that has been used for generating the that has been used for the domain generalization by having the style and content information from it and learn over the time. So we generate the image tokens into the prompt. We use the image tokens from the prompts, and we enable the prompt learning from the visual tokens for the style and content informations. So this is the cross interpolars which we have used, and the results we can certainly see that it for the frozen clip by using the frozen clip for both ResNet 50 and Vision VIT 16, the STYLIP outperforms by a fair margin. So these are the results for the left hand side represent the multi domain single target domain generalizations, where we have taken the five data sets into the account, whereas in the right hand side we show the results for a single domain multi-target kind of stuffs, where we show for the results for both clip ResNet 50 and Vision VITB 16 results. And then we try to see how the model performs across the domains for the domain generalization task. So we have taken let us suppose we have taken clipart base classes from the clipart as a training model, and then we have tested over the new classes of the other domains of the domain net, and we have clearly seen this that STYLIP outperforms other prompt learning like methods like co-op and co-op, even DPL by a very fair margin. And then we have taken we have compare STYLIP for the cross for the 11 data sets, and we have seen this that STYLIP and the other components, how it has been used and how it is effectively helping STYLIP to develop a better generalization method or network. So we have seen the results for the cross data generalizations, that is like we have trained the ImageNet, we have trained the STYLIP over the ImageNet data sets, and then tested over the other rest of the 10 data sets, and we report the average accuracy, and that is at least by 1 to 2% it has been increased. And these are the ablation results for the STYLIP, where we have taken COCOA into the account, and we have modified it, and we have modified the COCOA for the multi-scale features, and we've seen that multi-scale feature is certainly helpful for the domain generalization task, but still the STYLIP shows the better results than the MS COCOA and its other components. So and we have seen we have taken the different baseline results for the STYLIP. We have taken the late fusion projectors, average pool, and depth. We have taken depth of the projection layers, and how how the batch norm features are helping. So all this taken into the account, and we took as a different baselines, and we ablate STYLIP in a fair margins. And finally we show how much percent how much improve like increase in the computation resources, and how much it how much STYLIP outperforms the Maple and the Cocoa. So the by fair margin, by only a 0.18% increase in the parameters, we certainly outperform the various SOTA methods by a fair margin. So these are the some ablations related to like how intermediate layers, how change in the intermediate layers can affect the generalizations, the domain generalization part. And then in the below we can see the clustering of the clustering obtained from the text embeddings of the DPL and the STYLIP, where we can see the STYLIP is much have much better clustering as compared to the DPL. And then we took the context length into the account to generate to generate the prompt embeddings, and how this context length be helpful or can be altered to get a better domain generalization or the classification task. And when then finally we took number of trainings into the account to how STYLIP has been outperformed by like as compared to the different methods, and we have seen like it has been continuously improved over the iterations.